Good morning, everyone, and welcome to today's GoFly Master Lecture. As a reminder, GoFly is sponsored by Boeing and now includes a number of different partner organizations, as well as now we're up to just over 2,300 competitors worldwide, globally. So such a great community here. And today we're very excited to welcome Nick Lappos with us. So Nick is a senior technical fellow of advanced technology at Sikorsky Aircraft, where he oversees the introduction of advanced technology into new and existing products. He began his aerospace career in the US Army as an attack helicopter pilot in Vietnam. Nick joined Sikorsky Aircraft in 1973, where he has served in a variety of roles, including as program director for the development and certification of the S-92 helicopter. He also served as director of test engineering and as assistant chief and chief research and development test pilot, logging more than 7,500 hours of flight time and over 70 different types of helicopters. During his Sikorsky career, Nick participated in the development of aircraft such as S-76, UH-60, RH-66, and several others. A former designated engineering representative, flight test pilot, he has been a member of several National Academy of Sciences, NASA, AHS International, FAA, and advisory group for aerospace research and development committees, and holds 23 patents and 3 helicopter speed records. He's currently a member of the National Research Council, NASA Aeronautics Research and Technology Roundtable. Nick is also a distinguished alumni of Georgia Tech and a recipient of the Bronze Star Medal. We're very excited for his GoFly Master Lecture today. And without further ado, I'll pass it over to Nick.
Thank you very much, Paul. And for the team out there, please, if you will, accept that this discussion, and it is an open discussion, is attempting to convey some of the concepts that I've learned over the last few decades that have more to do with how to deal with running teams and how to get a good team of people working together and clicking to make the progress that's needed. I certainly don't want to be caught in the position here of recommending to you specifically how to design the machine you've got. I believe that to a great extent, you folks are very good at that game. And we're going to let you fly with that and not be shackled by the words that someone would give you across this video screen. The first set of concepts is that developing real machines is hard. It's one thing to have an idea and pen it down. It's quite another to actually produce a piece of hardware and have that hardware behave the way you want it to. I've had the fortune of working on the development in one capacity or another, sometimes as the leader of programs like these, the Comanche, the S-92, the Raider, the S-76, and a couple of detailed, what I'll call screwball, one-of-a-kind research aircraft. But they all provided lessons on how people work together to get something done. And so that's what this talk is about, is how do people get together to get things done. And what are some of the ways that you can adapt some group dynamics that help to let that happen? I'll invite you to recognize too that as I'm discussing, these are lessons learned, so that we actually had problems on programs, and it turned out we had to backfeed those problems into a new way for a program to run in order to be successful doing it. And I'll try and use those anecdotes as we go along from my own experience and from the experience of others who I respect. So without much more, let's talk about these basically 10 rules that I think you can apply. The first rule is you're the expert. Don't let anyone else tell you that you're wrong technically. No one else knows what you're doing. So have the confidence and the courage. And I'll use Musk as an example of this, being told that what he was doing was too hard in any one of 2 or 3 different endeavors. And as a modern Edison, he's leading teams that basically do what other folks say can't be done. And I have a joke that says basically, if this thing were actually easy to be a Scout Merit Badge, there'd be a cookbook way to do it. You'd go out and do that cookbook. We used to call them science experiments when I was a kid, and they weren't. You read it out of a book and you did something that demonstrates the scientific principle. What you're actually doing now is quite complex. I put a couple of quotes here because this is Mitchell was the designer of the Spitfire, talking to Jeffrey Quill, who is the the project test pilot on the Spitfire. And Mitchell basically said, if you talk to somebody about something and they tell you in a way that you can't understand it, or if they say it's too hard to explain to you, you know they don't understand it. Almost everything we're talking about boils down to fundamental physical principles, which can be understood, if properly explained, to any intelligent person. And this is a picture of those aircraft that I was talking about. I trust this slide set will be available to folks and be a handout. Okay, so you're the experts. And I wanted to put the one quote in there from Isambard Kingdom Brunel, who was a tremendous inventor in England and one of the people who helped adapt the world to steel and to iron as a new material. And he said in that quote at the bottom, that I'll just simply paraphrase, that he wouldn't give people rules for how to do things because he would be embarrassed if next year somebody come up with a better way to do it. So Brunel said, what I think I'm going to tell you is you're the experts and not us. And if somebody else tells you how to do your job with regard to the details of what you're doing, don't listen to them. You go follow your dreams, follow your ideas. And if you fail, fail brilliantly, which is really the second tip. Second tip is do something truly attainable. Take one or so hairy goal, something that is hard to do. And I know you're going to do it. I know that the contest rules actually call for you to have to do it. The suggestion I have, though, is that don't have more than one or two hairy goals, because the intersection of the Venn diagram of the success of a couple of stretch goals gets a tinier and tinier area of success. So pick one big one and go for it. And I'm going to offer some examples of goals like this. When Charles Lindbergh worked with Don Hall, who was the chief designer of the Ryan Airplane Company, to design the Spirit of St. Louis, their goal was to create an aircraft that flew further than any aircraft had ever flown before. And an index of that is that when they built the Spirit of St. Louis, after 11 and a half hours of flight test in St. Louis, racing to get it done, because the Ortig prize was very much like this GoFly prize. And they in San Diego flew for about 11 hours over a period of about a week. And when they finished, Charles Lindbergh climbed into the Spirit of St. Louis, filled it up with gas, and flew from San Diego, California to St. Louis, Missouri, which at the time that he landed in St. Louis was the longest flight in the history of mankind, after 11 hours of flight test. So I offer up that you pick one big goal and go get it. That quote at the bottom is from a friend of mine. I happen to know Jackie Stewart, the race car driver. And he one time answered to someone who asked, are you scared when you're driving? And he said, if you're not scared, you're not driving fast enough. So go scare yourself and pick one big, bold gesture and go get it. Tip number 3, when you do decide to define your vehicle with the fewest number of critical performance parameters that you can come up with. Your key performance parameters should define your design goal. My suggestion would be that no experimental prototype aircraft should have more than 4 or 5, because what happens then is, as you increase the number of critical parameters, you decrease the design space tremendously and make it much harder to make a quick experimental airplane. The goals should be sharply pointed, and you should attain only those goals. Don't overextend. We use the word creeping excellence. Somebody comes up with a bright idea 2 weeks after you freeze the basic design requirements, and then you begin to move towards that bright idea, and you discover people dropping what they're doing elsewhere and going in that direction. And very quickly you lose the focus that is very much a part of what we're trying to do with these machines, which is to make the machine do exactly what you want it to. So avoid creeping excellence. And that is at every level of the team. Now, there's an opposite side to that. If you come up with a really bright idea that falls within the scope of what you're doing, but increases the capabilities of the system has to have the elasticity to let you at least discuss that with the design team. The more conservative the team, the less likely even those good ideas will get into the fold. It is not a bad idea to finish with the KPPs you started with and succeed because you stayed only to those. So I recommend that kind of very strong discipline as being very important for the team. And yeah, I think you're going to hear that word discipline again and again in this discussion. Tip number 4 is organize every task. The joke is that the problem you're trying to attack, let's face it, it's the endurance of a vehicle, it's the weight closure of the vehicle as it flies. That's probably not the problem that's going to get you. Almost every team that fails because they described something to each other, and then when they built it, it didn't work because it didn't fit together. and that you'll discover some of the most mundane things. The latches that hold the cowlings closed pop open, the cowling jumps up and hits the rotor, and the aircraft has a real problem, and you damage your blades, and it takes so long to make a new set, you fail. And so you can actually look at that and say, well, my goodness, because of that, you failed. We had one aircraft that could go almost 300 miles an hour. And believe it or not, we couldn't make 300 miles an hour because the hinges on the rudders were made of aluminum, and they reached their endurance level at about 290 miles an hour of cruise speed. And we couldn't get to 300 because the hinges were made of aluminum, and it took too long to fabricate them out of steel and make the appropriate changes for that to go in time to book the speed that we needed for a critical performance review. And so, I mean, the idea that a rudder hinge is going to set the speed of a major configuration change, that shouldn't be. So the point I'll make is that every task has to be organized. And that means that you have to have a fundamental schedule and an assignment of capabilities that runs all the way down to each person knowing what they're doing and how they work with each other. A big important part of it. And I'm going to get onto this again in a little bit here. It's all about people, time, and money, and it's almost exactly in that order. If you've got a great idea, you'll probably find the money that you need. There are folks out there who recognize a good idea, and if you're good at selling it, you'll get there. You also will find good people, because a good idea will attract good people. The one that's the hardest thing to track in this is time. You can't make time. Time is there as the biggest problem you've got, and every day is a tick-tock. I used to keep, when I ran programs, a program clock that read 0 when you were at the end of the program. That was the scheduled time for it. And I put that clock up and synchronized them all over the design area so everyone could watch it, how many hours, minutes, and days that they had to close their piece of the pie. Pick hard workers as the doers. Almost always it's the workers. You'll find a lot of smart people. And I think in your career, you'll discover there are a lot of smart people who have great ideas, but aren't necessarily very good at getting them done. And there are people who maybe aren't quite as brilliant, or at least don't seem so in the way they talk, who end up getting stuff done. Recognize the difference. And if you will, I would suggest put the hard workers as the doers and put the smart people as the staffers, so their ideas get staffed out to the doers. There's a joke that goes on. It was said that Erwin Rommel was a German general and a very good selector of people, could judge people. And he said that in discussions with those he was mentoring, that there are 4 kinds of people, and they're judged by their amount of industry and their amount of intelligence. And what he said was, you pick your industrious, intelligent people, and those are the ones that you give the jobs to do. Those are your operational people. You pick your intelligent, lazy people, and those are your staffers that help to get the ideas out to your operational people. You pick your unintelligent and lazy people, and they'll have a certain percentage of them. Watch them carefully, give them something to do, and as much as you can, goad them into progress. And you would take your unintelligent and hardworking people and shoot them at once. As we go on here, every critical line item has a single owner. That's a very important thing. What you find sometimes is we have an ability to point a social team, an integrated management team that has some particular job, and that team is assigned the job. But unless you have a person's name on it, it's very easy for each team member to think someone else is doing it, or to shrug and say, well, I don't know why it's not getting done. Gee, we're all working hard at it. The suggestion I have is every single task has the name of a person. And then when you construct your integrated master schedule, your IMS, you would take that person that you have for each task on the IMS and ask them when they can do it. Don't tell them, and don't assign a schedule that they don't buy, because a schedule that is just handed to them is not theirs. There has to be that buy-in. And so with an integrated master schedule, the suggestion I have is every line item on the schedule, every milestone on the schedule has the name of an owner, and the owner has bought the position of the milestone on the schedule and says to you clear-eyed, I can do that. Now, there's something else you do when you're dealing with schedules like this and with assigning tasks, is assign them all personally and physically. It is okay and wonderful to have a tracking document. It's okay to have it in a file on a drive, and to tell everyone the master schedule's in the schedule drive on the IMS page, and let everyone go find it, and there you are, there are your assignments. But in the end, it is you and the eyeball and a handshake to that man or woman that you've given the task to that is how it gets done. Because we remember those personal commitments and that look in the eye much more than we remember a red item on a stoplight chart that's buried somewhere in a drive. So remember, this is all very personal. Time is your enemy. You can't buy a day. So you have to work to get back every day you can. One thing I'd suggest here is that you must always tell the truth to each other. You have to confess what's going on. You have to say, look, I'm behind. I can't get this. Two more items are supposed to show up from the supplier. They didn't show up. I'm behind. All that stuff has to be discussed as it happens. And you have to have the ability to expose your weaknesses to everyone around you. Because if you don't, then it ends up that the system will try and march on, and people will think they're where you are because they're looking at the schedule documents. And it's not where you are. So let's please that you have to tell the truth to each other. I'm reminded of this. I am a student of history, and I read a bunch about the formation of special operations troops. The first special operations troops in history were actually Rogers Rangers, who were formed during the French and Indians War under Colonel Robert Rogers. And he had a rules for his people that told what they were supposed to do. And what his fourth rule was, never lie to another ranger. Everyone tells the truth to each other. If you start to fabricate, if you start to brag, if you start to fail to confess, then the team together fails. So the suggestion I have is, it is more value to bring to the table when you have your daily meetings that you've done something and it's not working than it is to say that it's going well. So be sure you tell the truth to each other. Tip number 5, and this is very important, especially for small efforts, and I think the Go Fly Prize might represent a whole bunch of small efforts that are relative to a 200 or 300 person engineering organization are relatively small. Relative to what you're trying to do, though, they can be a substantial team, 10 or 15 members. And the suggestion I have is that everything is done in one place. And what you have is literally their test benches and your aircraft, the place where the rubber hits the road, are directly related to where the engineers are. The most successful teams I've run, the engineers were down in the hangar. The shops were right off the corner of the hangar with the right power and other fabrication capabilities. And the aircraft was right there, so that you ended up where everyone was in a team, and a person could try to fit something onto the aircraft, turn around and find the design engineer 50 feet away and talk about it. And the two talked it in. I have said in the past that we can often find out the difference between successful teams and unsuccessful teams is often the number of steps from the engineer's console to the aircraft. And so I invite you to have this golden triangle. This also means, though, that every morning at 7, 7:30, 8 o'clock in the morning, the whole team gets together and gathers in a circle. Whether it's 5 people or 50 people, you gather in a circle and talk about what you're doing. And somewhere in that circle, you would have the master schedule laid out, and everyone gets a chance to point to what they're doing. And this is the time when you tell the truth, and the time when you admit that things aren't working the way they should, and you need help from the rest of the team, because you'll get that help and it'll make things work. Tip number 6, and I have this is my own proclivity. I've often seen risk cubes, like the one shown in the multicolored cube at the bottom, as being the way to control the risks that occur. And risks, by the way, are really just a fancy name for a future problem. That's basically, you think you have a problem and you're gonna have to prove that you don't. And the risk cube is terrific for telling you how important the problem is to your program. And that is the likelihood of the risk occurring versus the consequence of the risk occurring. I mean, the likelihood might be only a 1, but if the risk is, for example, that the wing spar or the rotor blade spar can potentially fail under the loads in question, then that is an enormous consequence and has to be addressed. So the risk cube does give you at least a chance to identify the highly consequential and more probable risks and understand how to deal with them. But my suggestion is, and it's not actually explained in most places, what really happens is that every single risk on the risk cube ends up becoming a knowledge point on your IMS. And I show here on the left side a cartoon of an IMS, a master schedule that shows that and I hypothetically say it might be the battery and energy density might be one of your most important things, or the battery cooling, or some hybrid power supply capability. And there's a knowledge point in time which is achieved when actual hardware in a relevant condition can be shown to be proven that the answer is yes, that will work. So that is a knowledge point. The knowledge points appear on your IMS, and this is what you brief on the morning briefings, is all of your individual knowledge points. How everyone is moving towards the closure of their problems and the actual demonstration, first on the bench and then in the aircraft. So the suggestion I have is risks don't just belong on a cube, they belong on a knowledge point plot as part of your master schedule. And once again, that knowledge point is owned by a person who runs that team, and there is a natural outcome. If the knowledge point is achieved and you discover that the system does not work the way you want it to, that there is an offshoot, that somehow there's a plan B. And if you don't meet that KPP with the knowledge point on the system you've got, that there's a way around it. It's a dirtier way, it's a heavier way, it's a more expensive way. It isn't as sexy as the way you had planned, but it is, however, going to achieve what it needs to achieve. So that means it's going to give you the ability to close the problem and fly the machine. And often you'll discover that if that plan B consumes more weight or consumes more power, that you have to have stretched somewhere else in the system to make up for it. But you have to have those knowledge points defined, and that those off-roads, it's conceivable that if the knowledge point is powerful enough, that the plan is that you failed. But certainly we don't accept that. Certainly we run back to find ways around that. And I'll describe to you as we go on here some of the programs that I've been on that have had what amounts to abject failures of critical subsystems, which succeeded anyway. Tip number 7, and this is very important, and it's very important because I think engineers all want to have more data. Decisions drive everything. So be bold and make the decisions that you have to at every level. And I would suggest that you drive the decisions down in the organization to the place where the real knowledge is. Raise a culture where people do not come up to you to say yes when they already know the answer has to be yes. In fact, what you have to do is always, even if they bring you the problems and ask for the answer, you ask them for the recommendation. That always the decisions have to be made at the level where the detailed knowledge is there. I'll offer the Challenger accident as an example, where the space shuttle had the cold O-ring problem. And that was where the knowledge existed at the level where decisions could be made. But somehow there was a belief that those decisions could only be made at 2 or 3 levels higher in the organization. And as that information was brought up into the organization at higher and higher levels, the details were machined off until there was not enough information to make an intelligent decision, and therefore the wrong decision was made. So the suggestion I have is make sure that your organization is powered right down to the bottom. And part of this too is something that came up. We had a great discussion, Dan Newman and I, just before we came live here, and that was a question of how do you deal with dissension within a team? And the answer is the team must have dissension. Your daily meetings and your discussions on the IMS, argument is absolutely essential. When I said to tell the truth, that means you tell the truth in every way. But that doesn't mean they're destructive arguments. It means they're constructive laying out of the way things appear for each team member. Now, the younger team members will have more difficulty with the idea that they can think they're correct, lay out their decision on the table, tell everyone else, this is what I believe, and have the system decide not to obey that particular item, but to move in another direction. And part of this is to recognize then that there has to be some reasonable subservience to the whole. We don't bargain out safety, but you can bargain out whether or not you're right, and then seek the next knowledge point to know whether what you really guessed at that point comes true. And so what you can often do is you disagree across the table, you roll over and say, okay, we're going to go with the way you said it, and even though we disagree, let's do this, let's make a side bet and write down the disagreement. I say it's going to end up being 14 degrees too hot. You say it's not. And write it down and pin it on the master schedule. And when you get there, buy the other person a beer if they win, or you take the beer if you win. And you get a free I told you so. And that way you bookkeep differences in a manner that doesn't stop the program and that keeps things moving along. I'm reminded of fine football teams where there's strong personalities and competitive people. And football players often can decide how they're going to move forward competitively and pass the ball to someone else and recognize that that makes the team go further ahead. So the important thing here is to drive within the team dissension, disagreement, and truth-telling, but also then decide when it's time to pack up and move together to that next place you have to be. Now, the last bullet on here is something extremely important. You have to recognize the difference between a decision and a foregone conclusion. Many times, engineers are taught to nail things down to the nth degree. And we often do trade studies that get down to fractions of a pound. And we have to recognize, especially in a rapid prototyping plan, that there may be virtually no difference between the 2 or 3 places that we're discussing, except down at the 4th level. And you have to decide when it is that you're close enough that you can make a decision, freeze the design, and move on, because that's how you buy back time. The space between a decision and the data that is a foregone conclusion is the space that we all make our living. So I invite you, please, to have the discipline to recognize that and to reward it when people make decisions early. This tip number 8 is the most important of all of these, and that is fly, fix, fly, and then win. And that is that you fly and discover problems, and every time you discover a problem, it is golden. Because when you have a problem, that means you need to get the fix in, but once you do, that problem evaporates and it's gone. So bench everything you can, and that is to run things in a relevant environment as quickly as you can, fly them as often as you can. And that every time you fly and every time you bench, you're running an experiment that's worth more than any analysis you have. I'm going to get into a little bit of detail later on about the difference between the analysis and the actual airplane. But in point of fact, you have to remember that whatever you did as a design analysis that gets the system to where it is, where it flies, is no longer valid. The aircraft is the valid point. The bench is the valid point. The data you get from them is worth far more than the data you had in your analysis. Failures teach more than success. Every time you come up with a failure, there's an important point here. Design teams often have code and often have analyses that tells you what the design should be. When you fly the machine and discover the design doesn't quite work, that things fall short, then you realize the code you use is wrong, that the modeling was wrong. And there's a tendency for a design team to believe that the flight vehicle now should be used to support the changes to the design methodology, and that you'll actually run experiments on the flight machine to feed the code that is now producing the design, because that code will then produce a more elegant solution and fix the problem. I must avoid, as much as you can, avoid the idea that the aircraft is subservient to the design code. If something is too hot and your code said that you had enough cooling, then the answer is more cooling. That means a bigger cooling fan, a larger cooling core, a different type of cooling core, another extra cooling core, and it doesn't mean go back to the code and find out where the errors were. You can do that later, but don't hold up the program getting more data to feed the code, when in reality, all you have to do is increase the cooler area to make things cool enough. I'll offer an example of this. The S-76 ended up where we had the engine oil cooler blower fans were very high efficiency fans, but because they're high efficiency, they were close to their stall margins, which meant that as we started the aircraft, it was a spooky thing. If we start number 1 engine, it would run cool and be perfect. If we start number 2 after number 1, number 2's fan couldn't push its air past the stream that number 1's fan had established in a Y duct, which meant that the number 2 fan stalled. So the number 2 engine didn't get enough cooling and overheated. What we found was we could actually overheat whichever engine was the second one to start. We spent about 3 weeks trying to mess around with oil cooler blowers before we realized we were not running the S-76 oil cooler blower experiment program. And what we then did was to install 2 electric motor driven oil coolers in the baggage compartment of the aircraft. And those 2 coolers cooled both engines far more than the basic design. Of course, they weighed, that whole system weighed about 120 pounds, was sitting in the baggage compartment. If you look at the earliest pictures of the S-76 flying, you'll see 2 slots on the left side of the baggage compartment where those blowers blew the air out. We flew with those coolers for about 4 months while we perfected offline the right blower systems for the normal cooling of the engines. And then once we had the engines coolers designed properly, we dropped them back in, took these extra baggage compartment coolers out, and away we went. So that experiment that we had proved that the coolers didn't work. And what we did is quickly put in a crutch that fixed the problem while offline and without delaying the rest of the aircraft, we could find the way to get the coolers done. I can point out 50 different things like this where you'll end up with a flight vehicle that is marginal. And the suggestion I have is to come up with an experiment that makes the flight vehicle less marginal, but may add weight or cost or drag, but is a great short-term experiment to keep you flying. And here's why. When you're flying in this concept of fly, fix, fly, you'll discover that you have undiscovered problems elsewhere that have to be found by getting the envelope expanded to them. If a system like a transmission or a cooler or a bad landing gear won't let you get to the other places in the envelope to find those other problems, then you are delaying the ability to solve those other problems, and you're moving your schedule out dramatically. So the way to do it is to crutch the aircraft and put things in the aircraft that are not production worthy. They are not going to get you to the Go Fly prize, but they are going to allow you to fly with this cobbled up fix for a few more weeks or months, until you get the long-term solution on that major problem. But in the process, you've taken the aircraft to higher speeds, higher altitudes, more endurance, and discovered other problems that you could then fix. The whole object of a fly, fix, fly is actually to recognize that you probably will have, if you have 100% design new, then 95% of that design will work pretty well the first time, but the 5% won't. So if you have 100 parts, there are 5 parts that can be a major problem. And that means that you can fly experiments in those 5 parts, and each one of them gets solved offline. I put down here, no such thing as an isolated failure. If you're flying along and you discover a problem, nail it. Get some data, fix the problem. You can't assume the problem's just going to go away. It never goes away. That's what I mean by an isolated failure. It is not isolated. It is endemic to the design itself. And this is especially true if you're building a system that's going to go on for into production, build thousands. And by the way, I think that the Go Fly Prize is actually the beginnings of a whole new industry. So recognize the fact that even though you're doing some sort of an experiment that's going to go win a prize, that in reality, there's something behind that that will be of great benefit to you and may be monetized. And so let's recognize that you want to try and solve those problems as best you can. Every problem has at least 3 solutions. And the suggestion I have is when you start fixing a problem, especially one that's a major problem on your risk cube that could stumble the entire system, don't just fund and don't just try one solution and bet on the solution. It might take 3 weeks to come up with that solution. In that 3 weeks, you could have had 2 other solutions being tried, and the one that actually works gets put in. Because if you try 3 solutions and one doesn't work, you have bought the time on the other solutions. 2 or 3 weeks have been spent on them. I recognize that there's people involved with these, so that means that you have to have a team large enough to be able to have multiple solutions being tracked. And this also means you also have to have the configuration management to recognize what those solutions are. And the last bullet is, if it's silly but it works, it's not silly. I'll offer an example. On the S-76, we had a problem with the tail rotor where there was a bonded joint where the tail rotor cuff joined the tail rotor spar. That bonding cement was not working well on one of the models. And we decided, rather than start playing the tail rotor glue experiment instead of the S-76 development experiment, we simply put 4 bolts in it. And do you know that to this day, there are S-76 tail rotors that have 4 bolts nicely covered over, and they look smooth, but there are 4 bolts in the middle of the tail rotor blade at about 50% span. And you would say to yourself, now, is that the way to make a nice flying wing, is to have big bumpy bolts in the middle of it? And the answer is yes, if it works. And so I offer up that if it's silly but it works, it's not silly. Now, experiments are worth more than analysis. I mentioned this earlier, and I'm going to spend a little bit more time on this. That, by the way, basic research is what I'm doing when I don't know what I'm doing. That's a Warner von Braun. You don't really know what's going on until you fly it. And when you fly it, things aren't going to work. There is a tendency for design engineers to focus in on trying to fix their tools and to burden the program with more data on the problem and more flight testing around the problem so they can feed that back into their code and fix the code. And the suggestion I have is explain to design engineers as best you can that they have to come up with a fix. Remember, define 2 or 3 of them. And those fixes have to be put into the aircraft, and they have to work. And that what counts is the aircraft, not necessarily the code. Later, you can doctor the code. Get the data you can, and then fix the code after you win the prize. Okay. Now, important to mention too, if you have 2 or 3 fixes that are going in and you're going to try each one of them, track the fixes and make sure that the configuration control documents reflect what fix you have. This is a science experiment, and very much there has to be controls, and there has to be an understanding of what change was actually made. So please recognize that and keep track of those fixes. I put there the quote from Charles Kettering. This is one of the most fun phases of any program, is finding out things don't work and then fixing them. Problems are the price of progress. Don't bring me anything but trouble. Good news weakens me. That's Charles Kettering. If you know who Kettering is, please do a little Googling. Kettering was one of the principal researchers on automotive technology and ran the General Motors research labs for a period of about 13 years. And Kettering was holds about 300 patents that have to do with automobiles. I'll offer some examples. One of the things that Kettering did was design the electric starter. If you can believe this, the hand crank starter was on cars because everyone thought that sizing an electric motor that would turn over a car and start it would be too large. In fact, there were erudite papers written by folks from august Boston universities to prove that the electric motor to start a car would be almost the same size and weight as the engine of the car, and therefore was impractical. And what Kettering did is he looked at the design requirements and said, now wait a minute, the rules for designing electric motors are that the motor has to be a continuous duty. And a continuous duty electric motor that put out the horsepower needed to crank a car engine would be about 1/2 of the weight of the entire car engine. That's totally impractical. But then he also realized that the car engine started in about 5 seconds. So he said, why don't we just make the duty cycle 30 seconds or less? And the minute you took the heat curves for electric motors from continuous down to 30 seconds, the motor shrank to about 5% of the size of the motor that was previously sized. And therefore, starter motors became practical. Charles Kettering came up with that concept, built the first starters for cars, and in the next 2 years sold 1.2 million starters. Just think about that. Now, configuration management is key to the experiment control. Also key to safety, and it's key to being sure that the machine you fly is the machine you think you're flying. I'm not going to go into a lot of detail on this. I'm going to tell you that it all boils down to that last bullet, which is you have to have a person, a systems engineer, an aircraft manager, someone who is capable, someone who is anal retentive, someone who will not let something on the airplane until it has the right design approval, and when it's on the airplane, it alters all of the configuration documents so we all know it's on the airplane. This is absolutely critical. It's critical for flight safety, but it's also critical for understanding how your experiment is running, because this person who runs this will also tell you, hey, when I ran that and the temperature was high, what cooler configuration did I have? And he'll tell you. And then say, well, what software load was there that drove the fan? And he'll tell you. Because all of that stuff is part of what that systems engineer, that aircraft manager, what he or she has decided is the right way to track the program. And by the way, this documentation calls for the right kind of software. I invite you to hunt for the software that will make that happen. You like my fancy water jug? By the way, speaking to you from a 5,500-foot plateau in Utah, where it's dry and comfortable. And today it's going to be up near 60 degrees. And after I finish this discussion with you, I'm heading out to the hangar to work on my experimental aircraft because I love to fly. Okay, here's a quote, and I had to throw it because I just love quotes. These alterations, will the mathematicians ever be clever enough to save us from this patching and experiment? One might think it's possible to calculate the whole thing out beforehand, the cost of it. This was a lament that was recorded in a science fiction story written by H.G. Wells. And this quote came out of that story, which was published in 1895, 8 years before the Wright brothers flew. So didn't H.G. Wells get it right? And by the way, this lament could be made by every program manager on every program I've ever worked on or run. And it is absolutely the fact of life. And it brings up something I must tell you. Build into your IMS the white space to do the whole airplane over again at about 50% of the time it took to get it to that place. In other words, presume you're going to make about 50% changes to the fundamental systems of the airplane as part of the flight testing before that airplane is ready to go face the prize. It is one of the tenets of all of us is that alterations are part of the configuration and they are part of our design. If you don't build them into the plan, it'll look like you're late when you're not late. I must also tell you that almost every program that I've been on, the published schedule that we show to people presumes that everything worked perfectly on the first flight. There's 6 months of proving how wonderful it is, and then you go into FAA certification. And I've never been on a program with that was less than 1 year of flight testing and experimenting. And it's 1 year because of the time it takes to get changes in. For the kinds of programs that you folks are doing, the kinds of wonderful, quick teams that you have, it could be just months, but it's certainly not days. It's certainly not weeks. Tip number 9, believe the data. Igor Sikorsky had a quote where he said that there'll be times when the theory and the fact do not agree. He said, I implore you young people to always respect the facts. Data wins. Everything boils down to data. When you're making decisions, have as much data as you can. And remember that thing about foregone conclusions versus enough data to make the decision. But get the data. Because if you don't have the data, you're going to move off on presuppositions. And then when you spend 6 or 8 weeks chasing based on your guess, and you discover it wasn't what you thought it was, you've lost 6 or 8 weeks. So remember that. You're always going down the path of shortening the time as much as you can. Tip 10, schedule is nearly everything. Keep your master schedule updated. Tell the truth to each other, which means that your master schedule is always going to move to the right. Our typical calendars move from the left to the right. So therefore, when the schedule moves to the right, you're running out of time. But if you have the white space built into the schedule, as you're doing that, you're actually doing what you plan to do. Pull anything you can to the left. If somebody can gain a day or a week, they'll get there. Fight for every day. A joke, we know it's Sunday when you hear church bells on the way to the hangar. There's 7 days a week and there's 24 hours a day. You must not work your individuals that long on flight aircraft, especially flight aircraft that carry people. So you have to have enough manpower to be able to run multiple shifts and enough data handoff so that each shift knows what the other shift did. There's less in the way of lost communication. But time is of the essence, and my suggestion is none of you will be 40-hour week. None of you. That's not the way this thing's going to work. This is actually the telegram at the last bullet, the telegram that went from Don Hall to Charles Lindbergh. Can build plane, delivery about 3 months. How's that? That's the spirit of St. Louis. As I said, that was absolutely earth-shattering. That was like SpaceX landing one of their boosters back down again on the pad. That's how important that was. And what a bold statement Don Hall made. Okay, tip 11, and this is something that I'm going to suggest for you. Yes, you're going for a prize. It's a terrific thing, and I want to compliment Boeing for pushing the Go Fly. This is a terrific thing, and I believe that human progress is made by these kinds of things because we're naturally competitive. But please recognize that what you're doing has the potential to be terrific, and therefore it could very well be something that goes into production. And when it goes into production, it's conceivable of things you had on your Go Fly demonstrator won't float when you have to go to the FAA or the CAA or EASA. Governmental qualifications are very important. So in your plan somewhere, worry about how you would track what you're doing here to what will end up being the final product that might go out. Even aircraft that fly to deliver pizzas as UAVs must have a safety analysis that shows you're not going to land in some nursery. Please understand that. So always have this as the back part of it. What is some recommended reading? I could go on and on like this. Reading is fundamental to everything we're doing. Kelly Johnson ran the Lockheed Skunk Works, and he wrote a great book called More Than My Share of It All, where he puts out his 14 rules, and I suggest that you give that book a try. Leslie Groves was the general who ran the Manhattan Project, and I would offer up that his book, Now It Can Be Told, talks about some of the things that he learned as he went along. A guy named Boyd wrote The Professional Amateur, which is a biography of Charles Kettering. I recommend these as being the kinds of things where knowledgeable engineers want to know more about what happened in the past. Let me offer an example of Leslie Groves, how to run a program. He had to build factories to separate uranium-235 and 238, and those factories needed enormous amounts of electricity. So they built the Tennessee Valley Authority and all those dams to provide the electricity necessary to run those factories. Well, building a TVA is by itself an enormous enterprise. But he found out that he didn't have the copper to wind the generators in the dams. That the copper was needed was being used to make brass for shell casings, and there was no copper to be had. Groves called a meeting of his team. He got the electromotive table out and looked at the electromotive table and realized that copper wasn't as good as silver. So they said, okay, we could use silver to make the windings, can't we? I said, yeah. And but they said, where are we going to get all that silver? And Groves says, don't worry about it. I can get it. He called up the Secretary of the Treasury and said, I'd like to borrow some silver from you. He said, instead of you storing it at Fort Knox, how about if you store it in my facilities? And the Secretary of the Treasury said, that could be done. And Groves says, let's do that. I'll just second it to me. I'll give you all the paperwork necessary to close it out. And they said, how much silver do you need? He said, I need about 10,000 tons. And the Secretary of the Treasury said, we deal in troy ounces. So Groves calculated how many millions of ounces it was. The silver is still in the windings of the generators in the Tennessee Valley Authority right now. And that's an example of how a team cannot even stagger a day in an insurmountable problem of there's not enough metal. And so Groves taught us how to run a program like the one you're running, maybe not quite as expensive. Okay, I think we've got a little bit of time for questions. Paul, do you want to help organize this?
Yeah, absolutely. Thanks for that, Nick. So got a couple questions in, two, both about team size. Whether you have any recommendations on how big is too big, how small is too small, and if you have any recommendations given the physical size of what the GoFly device needs to end up being.
You know, the physical size certainly does define a little bit. I've always said that a team should be no larger than that necessary for everyone to be able to touch the machine all at the same time. So if you picture how many people fit in a phone booth, that might give you an idea. And for a fairly small GoFly competitor, we might be talking about a 15-person, 10-person team. And I'm just now winging it. It's certainly not 2 or 3, because I think what you're going to find is if you have a small team, you're overworking everyone. And you don't have enough granularity in the master schedule to be able to be sure that one person can nail a problem. So the suggestion I have is look at your schedule, look at the technologies you're using, and decide how many line items there are and how many of these can one person juggle. The gut feel I have for GoFly is it's not a 50-person team. That would be awful. Is it a 15? I bet it is. Now, I'm going to say something along these lines too. Remember that your team also includes the suppliers that you've got. You're going to buy a motor from someone. You're probably not going to make your own motors. That person on that motor team is part of your team. And be sure that their schedules match your schedule. And be sure that they've made a promise to get something to you. You don't sit there and wait for the thing to show up on Thursday morning. When it doesn't show up, you say, what's wrong? You're tracking their schedule to deliver it to you the same way you're tracking your own schedule. So recognize that your suppliers are part of your team, and they're not included in the numbers I'm mentioning. The batteries probably will come from someone else. The hybrid systems will come from someone else. Major metals will come from someone else. All of those things are part of it. I hope that answers the question.
Great, thanks. And then the next question is about scalability. So lots of people in the past have talked about scaling things down from bigger aircraft. But this question is about scaling up from very small, more drone-like aircraft, and what your views on are on scaling from something that's very small right now to something that's a little bit bigger.
Well, scaling has a couple of scaling up has a couple of major problems. One of them is the fact that you build beam equations fundamentally, so that the loads that are imposed on a fairly small beam, and let's face it, the beam bending and beam stresses are L-cube functions. So as you begin to grow the length of the beam, you get enormously greater beam depth than you realize you could, because you're beginning to reach material problems. So that small rotors have extremely good strength across small radii. And then as you grow the radii, you discover the materials you're using cannot give you that same strength. And it also goes too with heat density. As you begin to get battery packs and grow the volume of a battery pack, you begin to realize where you get a small battery pack and the external surface area allows you to have a given heat rejection into the atmosphere. As you grow the volume, and let's face it, that's a dinosaur problem. As you grow the volume, the skin's area isn't great enough to allow that heat dissipation. So you end up going to much more active cooling and much lower efficiency. So I would suggest that scaling up to more than just a few percent, 20%, 50%, scaling up 2x, 3x is a major issue. And start running those experiments as early as you can to see whether you have that under control.
Great. So next question. Do you as a helicopter test pilot think it's possible to auto-rotate a GoFly size quadcopter multi-rotor all the way down to the ground with a safe outcome? Or could a computer do it? Any suggestions for being able to get safely back down?
Yeah, and those are great questions. And this is that scalability again. The actual knowledge as to how a rotorcraft auto-rotates and how to predict its auto-rotative capabilities is actually pretty well understood. The code that's there that looks at rotor inertias and looks at the disk loading for the rate of descent and the amount of energy available at the bottom to arrest the descent is all known. And I must tell you that it all falls into the question of disk loading, and it falls into the question of stored energy in the rotor inertia. Most of the quadcopters have fairly high disk loading. Most of them have very low rotor inertia. Most of them probably will not allow a full auto rotation. That's my gut. It is conceivable there are ways around that. I would also offer, though, that when you have multiple battery sources and multiple electric motors, that it's quite conceivable that a total power failure in a quad is an extremely improbable event. My suggestion is to attack that mostly from the probabilities and to handle any probable single failure and any improbable two failures and show how you can shuffle the problem off, maintain vehicle control, and make a landing.
Great, thanks. And then also hardware related, do you have an opinion on whether for GoFly electric servos or hydraulic servos would be better?
Wow. In scaling the size of the vehicle, I'm going to tell you, we're all moving toward electric. I'm going to believe that supporting a hydraulic system in a smaller aircraft may not be very necessary, and electric actuators work very well. And here again is the square cube law. The forces you're dealing with regard to the blade pitching moments are probably pretty well handled by electrics. But you know what? I said you're the expert on that, not me. I'm sure that the people who are laying this out now can begin to discuss the blade moments and the requirements. Gut feel I have, though, is that the complexities of hydraulic systems are probably not necessary until you start moving up to a 3, 4, 5 passenger machine when hydraulics seem to have some advantages.
Thanks. And then do you have any particular stories about experimental or one-of-a-kind aircraft that had a really big difference from the engineering plans to what was discovered during test flight?
It's funny. I have a slide that I can't show that shows the changes that occur on any particular production aircraft from the first flight to the delivery of the aircraft. And I must tell you that one of our commercial models that I flew as the project pilot on, every single rotating component in that model was rolled through at least 2 dash numbers and sometimes 3. And of course, a dash number means a substantial change to the blueprint. So it is safe to say everything changes. It is just a question of what a change is. The fundamentals, the aircraft I'm describing is the S-76. The first S-76 we flew looked very similar to the delivered aircraft. But if you actually go and look at the detailed design changes that took place, they were fundamental. And they went back into our engineering source code to help make the next design more successful coming out. I would have to say this too, that when you design for production, it's a different world than what you're doing for a prize. And so for production, you have sustainability, durability, and supreme safety over thousands of hours, and in the hands of less trained people than your experimental crews. Your experimental crews that get to know the aircraft well are probably capable of dealing with inspection requirements and lives of components that are minuscule as compared to what goes into production. So it's safe to say that your job is a bit easier from that standpoint.
Thanks. And then we're going to close with just 2 general questions. The first being, where do you think the future of commercial aviation is going?
I believe there'll be more than ever. I think when you hear Bezos talking about delivering pizza by UAVs, by the way, that's aviation. I cannot believe that commercial airlines and large helicopters going to oil rigs is the only thing that aviation is. It is my belief that the things that you're doing on the GoFly Prize, the things that others are doing to build small electric and hybrid systems are going to change aviation so that the number of flying machines, and that is, let me arbitrarily define it as something larger than a drone you buy on eBay, something that weighs 20 kilograms or more, that we're going to find ourselves in a place where 40 years from now, we have 100 times the number of flying vehicles that we have today. And that there will be the ability to carry 2, 3, 4 people, and that I can pick up the phone and get the drugs that my child needs at 3 in the morning, will be delivered to my doorstep in literally in 30 minutes. I think it's going to happen. And that, therefore, aviation is nothing but far and away larger than it is today. And that also means something else too. That just because they're automated doesn't mean there aren't going to be people who design them, who build them, who maintain them, who have the factories for them. I believe the number of jobs in aviation is going up tremendously. And those jobs are going to require people with good educations.
Great. And then as parting words for the GoFly competitors, do you have any particular words of advice?
Don't let anyone tell you you can't. Go do it. Go build it. And I'm reminded of Thomas Edison saying that the power plants had to be every 3 or 4 miles because direct current was very hard to transmit across wires, and that with direct current didn't sustain the ability to have high current loads for more than about 2 or 3 miles. And then Charles Steinmetz walked in there and said, how about alternating current, and changed the entire game. And there'll be those kinds of changes that you'll come up with, and you are the ones who will show us what the future is.
Great. Thanks so much, Nick. I'm sure that the GoFly community has gained a great deal from your master lecture today, and we really appreciate your time here.
Thank you. Thanks for the opportunity. Use my email if you have questions or comments. Don't hesitate to shoot me an email.
Great. Thank you. Bye.